Welcome to the deep dive. We're here to crack open complex topics, pull out those game-changing insights, really help you get what's going on. Today, we're tackling something fascinating, actually. It's a bit of an engineering mystery. How something as, well, fundamental as a steel I-beam.
The workhorse.
Exactly, the workhorse of construction. How can it hide these vulnerabilities?
Right.
Especially when designs get a bit more adventurous. You know, the recent collapse of the Albany County Rail Trail Bridge, for example, that was a really stark reminder. So our mission for this deep dive is to figure out why these kinds of failures happen, and maybe more importantly, how new research is helping engineers build safer, more resilient structures. We're going to look at some new studies, connect the dots to real incidents, and hopefully reveal some solutions emerging right now.
And it's such a critical topic. I mean, steel eye sections are just
Yeah.
everywhere. Skyscrapers, bridges we use every single day. They get chosen because they're incredibly strong, efficient. But you're right, as designers get more innovative, maybe trying to save a bit of material or achieve a certain look, they can stumble into these hidden challenges, even with components that seem so familiar. This deep dive, I think, will really highlight those critical issues that, if they're misunderstood, can have pretty significant consequences. Very real ones, as we've seen.
Okay, let's unpack this then. Why are steel I-section girders just so popular? What makes them the go-to?
Well, fundamentally, they're incredibly efficient, just a fantastic strength-to-weight ratio.
Mm-hmm.
You get loads of structural capacity without using heaps of material.
Mm-hmm.
Plus, they're durable, relatively easy to make, versatile. They really are the workhorses. But yeah, despite all that, they do have this particular Achilles heel, especially that thin middle part, the web.
The web, okay.
And that weakness is something called web buckling.
Web buckling. Okay, that sounds serious. Can you paint a clearer picture? What does that actually mean?
Absolutely. Imagine you've got a thin, stiff piece of paper, standing it upright, and you press down on the top edge. It might hold for a second, but if you press just a bit too hard, it'll suddenly wrinkle or bend right in the middle, right?
Mm-hmm.
Loses all its ability to stand straight.
Yeah, it just crumples.
Exactly. That's pretty much web buckling. It's when that thin vertical plate gets hit with compressive stress and it just sort of deforms, wrinkles unexpectedly, like that paper. And when that happens, the beam drastically loses its capacity to carry the load it was designed for.
So it's not just breaking, it's actually crumpling under the load. What are the common things that might trigger that?
Several factors can play into it. First, off-center loads. If the force isn't applied perfectly down the middle,
Adds extra stress.
precisely, those eccentric stresses can push the web towards buckling much faster. Then there's something called shear lag.
Shear lag. Okay.
Imagine you're, say, pushing a thick phone book from one end. The pages might not all move together perfectly. The stress might concentrate unevenly near where you push.
Ah, I see. Like uneven stress distribution.
Exactly. That's sort of like shear lag. Stress in the web doesn't spread perfectly uniformly, especially near things like bowl holes. Creates weak spots. The web's thickness itself is obviously key. The more slender it is, a big height compared to its thickness.
Less stiff.
Right, less stiff, more prone to buckling. And finally, web openings. Holes cut for pipes or wires or access. They just reduce the effective area, and the stiffness makes it more vulnerable.
So it's this delicate design balance. Now, engineers obviously know about this for standard beams. They add stiffeners, right? Or make the web thicker to boost stiffness. But here's where it gets really interesting today. We're seeing more and more use of steel beams where the depth varies. Why is that becoming common? What's driving that choice?
It's a mix of things, really. Sometimes it's about saving material, which also lowers the beam's own weight.
Makes sense.
Sometimes it's practical, providing space for utility services like ductwork or pipes to pass through. Or, like you said, sometimes it's purely aesthetic. Achieving a more modern look, maybe visually lighter, it offers flexibility. But this trend, especially when the depth changes abruptly, like a step, well, that's introduced a pretty crucial knowledge gap. And that's what this recent research paper really digs into.
A knowledge gap, so we didn't really understand what happens there.
Not nearly as well as we thought. Most of the buckling studies focused on prismatic beams, the ones with the same depth all the way along.
The standard ones.
Right. Or tapered beams, where the depth changes nice and gradually. But the behavior of stepped beams, with a sudden abrupt change in depth, that's been largely unexplored territory. So this paper focuses specifically on local web buckling right at that sudden step. It's a surprisingly critical weak point.
And just to clarify, most previous work on stepping wasn't even about the overall depth changing.
Correct. A lot of it looked at changes in the flange, the top and bottom parts, maybe their thickness or width. This focus on the total depth changing abruptly is relatively new and, as it turns out, really vital.
So testing these complex new designs, you can't just build dozens of physical models, right? That'd be crazy expensive, take forever. How do researchers actually study this stuff?
Right, exactly. Instead of building physical models, they use the power of computation. Specifically, the finite element method, or FEM.
Them. Okay.
Think of it like an incredibly sophisticated digital simulation. It's a numerical technique. It breaks down the whole complex structure of the beam into thousands, maybe millions, of tiny, simple pieces, the elements.
Like digital Lego bricks.
Sort of, yeah. And by analyzing how each tiny element behaves and interacts with its neighbors under load, FEM can accurately predict how the entire structure will respond. Will it bend? Will it buckle? Where? And a core finding from this study is just how reliable FEM is for this kind of problem. Often much better than relying on the old design code formulas, especially for these complex shapes. They really put FEM through its paces in this study. 3 main steps. First, they verified it checked its accuracy against known, real-world experimental results.
Okay, proof of concept.
Second, they used it to analyze that recent bridge failure we mentioned.
The Albany County one.
Exactly. And third, they did what's called a parametric study, basically playing with different design features in the simulation to see what makes the buckling worse and what helps prevent it.
That sounds thorough. When they checked FEM against the real-world tests and the existing design codes, what was the big takeaway? Anything surprising there?
What really jumped out was, first, FEM's accuracy. It was excellent. The predictions were very close to what happened in the actual lab experiments, maybe slightly overestimating the buckling strength, which is generally okay, conservative.
So FEM is a reliable tool.
Highly reliable, yes. But here's the kicker. The established design codes, they were all over the place.
Really?
Yeah, for instance, Eurocode 3, which is a major standard in Europe and elsewhere, significantly underestimated the buckling strength compared to the experiments, sometimes by nearly 30%.
Wow, that's a big difference. Underestimated, so potentially unsafe.
Potentially, yes, or at least not giving you an accurate picture. AISC, the American code, was closer in some cases, but still showed variability. It really raises a big question. Can we, or should we, rely solely on these standard codes, often based on simpler uniform beams when we're dealing with innovative complex geometries like these stepped girders?
It strongly suggests we need more advanced tools.
Definitely, like FEM.
And speaking of needing those tools, it's one thing to have a theory, another to see it play out tragically in the real world. That Albany County bridge failure, you said FEM didn't just explain it afterwards, but accurately predicted the buckling. How close was that prediction?
It was incredibly, almost chillingly close. Yeah. So July 12, 2023, Slingerland's New York, this new rail trail bridge they were building, major collapse.
During construction.
During the casting of the concrete deck, yes. The main steel girders buckled quite dramatically, sort of hinged inwards and collapsed onto the retaining walls below.
Wow. Anyone hurt?
Thankfully, no. It was incredibly fortunate. But the county's investigation later pointed straight at a design flaw. The new bridge design mimicked the old one's layout, but the new girders had this abrupt step transition in the top flange, going from a deep section to a shallower one.
The exact thing the research is looking at.
Precisely. And crucially, unlike the original bridge it replaced, this new design didn't have any support directly underneath that step transition point. A critical omission.
Can you give us a sense of the dimensions involved?
Sure. The whole span was around 42 meters. The deeper middle section was about half that, 21 meters or so. Depth went from about 1.6 meters
Pretty deep.
down to just over a meter the shallower parts.
Okay.
So roughly a 2/3 depth reduction. And the web, that vertical plate, was only about 10 millimeters thick, relatively slender.
Okay.
So when the researchers modeled this specific bridge failure using FEM, the simulation showed web buckling right at that abrupt step as the primary, the first mode of failure.
And the
The predicted buckling load from the FEM analysis was almost identical. I mean, really close to the estimated weight of the wet concrete deck on the bridge at the exact moment it collapsed.
Wow. That's profound. It's not just theory then.
Not at all. It's a powerful validation. This case study really hammers home the paper's main conclusion. For these complex steel geometries, doing an advanced buckling analysis, like with FEM, shouldn't just be an optional extra check. It probably needs to be mandatory in the design process.
A real wake-up call for the industry.
You could say that, yeah, if we want to prevent these kinds of failures.
Okay, so with that critical link established theory matching reality, what does this mean for designing future stepped girders? The paper then dives into that parametric study you mentioned, right? Stress testing different design factors.
Exactly. They set up a base model in the simulation and started tweaking things.
And one key finding straight away was that buckling happened early.
Yes, often at very low load levels, well within what we call the elastic limits, meaning the steel wasn't even close to yielding or its ultimate strength when the buckling initiated. It's a stability issue, not just a strength one.
Right. So what about the step height itself? How much does that sudden change matter?
Well, interestingly, for uniform girders, a slightly counterintuitive finding was that making the web taller could actually lead to a lower buckling load in some cases.
Huh.
But for the step girders, the critical thing was that local web buckling consistently happened right at the step location, on the deeper side of the step, almost regardless of where the main external load was applied.
So the step itself is the weak point.
It creates the weak point. And here's the curveball from the research. The exact amount of the step, the height difference, wasn't the most critical factor, surprisingly. Once you had a step, you had a problem.
Really? So a small step is almost as bad as a big step.
Not quite that simple, but the buckling capacity was significantly lower than a uniform girder, even with relatively small steps. What happens is that step disrupts the smooth flow of stress in the top flange. It forces that compressive stress down into the web right at that point.
Creates a stress concentration.
Exactly, which leads to buckling there. The key insight was, once the step height gets bigger than about 10% of the section depth, buckling at the step becomes the dominant failure mode. And the buckling strength drops off quite sharply as the step increases, maybe up to about a 50% depth change. After that, the effect kind of levels off. But we're talking reductions in capacity of, more than half, sometimes up to 70% compared to a uniform beam. It's significant.
Okay, so any significant step is a major concern. Now, does it matter where that step is located? You mentioned top flange versus bottom flange earlier.
Yes, and this is a really critical design takeaway. Huge difference. The study compared putting the step in the top flange, which is usually under compression,
Right.
versus putting it in the bottom flange, which is usually under tension. The finding was clear. A step in the lower tension flange had a much, much smaller effect on the web buckling capacity.
Interesting.
Yeah. The buckling still happened where the main load was applied, like in a uniform beam, and the actual buckling strength was very close, nearly identical to the uniform girder strength.
So the implication is huge.
It's massive. Just by moving that required depth change from the top compression side to the bottom tension side, you can potentially restore almost all of the lost web buckling capacity.
That's a really practical piece of design advice right there. Okay, what about the ends? How the girder is supported. Simple supports versus rigidly fixed ends.
Another really powerful finding emerged there. For standard uniform girders, it's expected. Fixing the ends provides more restraint, so it increases the buckling load, makes it stronger against buckling.
Okay, that makes sense.
But for the stepped girders, having fixed supports was a total game changer. Remember how the simply supported ones saw their capacity plummet?
Yeah, by like 60, 70% sometimes.
Right. But the stepped girders with fixed supports, they only saw a pretty modest reduction in buckling strength compared to a fixed uniform girder, maybe only around 10%.
Wow. Why such a big difference?
It's because fixing the ends changes the overall bending pattern in the beam. It reduces the bending moment near the middle, and crucially, it reduces the longitudinal compressive stresses right at that step location, especially if the step happens to be near what's called an inflection point, a spot where the bending moment naturally drops to zero.
Okay.
And this suggests that maybe some of the current design code formulas for web buckling, which often don't explicitly factor in the bending moment or the stress level at the buckling location, might be missing a really important piece of the puzzle for these complex step beams.
Fascinating. So given all these vulnerabilities, the step itself, where it is, how it's supported, what about strengthening, adding stiffeners, what did the research show there?
Right, this is where we get into practical mitigation strategies.
Yeah.
The study looked at several different ways to add stiffeners right around that critical step area. They tried vertical stiffeners, some short, some running the full depth of the web. They offered some help increasing the buckling capacity, but honestly, it was pretty modest. Maybe a 20% to 70% increase over the unstiffened stepped beam, which sounds okay, but is still way below the capacity of a uniform beam.
So better, but not a complete fix.
Not really. But then they tried a horizontal stiffener, just one, running along the web near the step.
Yeah.
That was the winner. By far the most effective single stiffener. It increased the buckling capacity dramatically, almost bringing it right back up to the level of the original uniform girder.
Really? Just one horizontal stiffener.
Yep. It essentially prevented that local web buckling from happening. Any failure then shifted to a different mode, involving the flange and web interacting at a much higher load. And if they combined a long vertical stiffener with a horizontal one, that completely prevented local web buckling altogether.
Mm.
Failure then occurred in the stiffener itself, but at a very, very high load.
Why is the horizontal one so effective? What's the mechanism?
It comes back to why the buckling happens at the step. Remember, the step discontinuity forces compressive stress horizontally into the web at that point.
Right, the stress concentration.
Exactly. The horizontal stiffener is positioned perfectly to directly resist that specific horizontal compressive stress. It provides stiffness right where it's needed most to counteract the primary cause of buckling in this specific scenario. Vertical stiffeners help generally, but the horizontal one directly tackles the root cause at the step.
That makes perfect sense. Now, it's always important to acknowledge limitations. Even great studies have boundaries.
Right.
What did this research identify as its limitations?
Indeed, they were careful to point that out. One thing is idealizing the supports, assuming perfectly simple or perfectly fixed ends. Real-world supports can be more complex, especially if the girder is part of a larger building frame. That interaction could change things slightly. Also, in reality, different types of buckling can sometimes interact in complicated ways. It can be tricky to perfectly isolate one specific failure mode in every possible geometry. And for future work, they suggested looking more closely at something called numerical singularities, basically quirks that can pop up in the math of the static analysis, and how they might or might not influence the buckling analysis results, just refining the computational models even further.
Understood. Well, this has been an absolutely incredible deep dive. We've gone from a basic steel beam to these hidden complexities and step girders, linked it to a real-world failure, and uncovered some really critical insights for structural safety.
It really ties together nicely. So to summarize the key takeaways for you, our listener.
Yeah.
First, steel eye girders are efficient, yes, but ones with abrupt depth changes are seriously susceptible to web buckling right at that step. Their capacity can be much lower than uniform girders.
A hidden danger.
Second, finite element method, FEM, is a vital, reliable tool here. It often outperforms standard codes for these complex shapes. Using it for such designs should probably be standard practice, not an afterthought.
Right. Use the right tool for the job.
Third, smart design choices can make a huge difference. Moving the step to the bottom, tension flange, helps immensely. So does placing it in areas with lower bending moments, if possible. And crucially, adding horizontal stiffeners at the step is incredibly effective at restoring that lost capacity.
Very actionable insights.
And finally, that Albany County trail bridge failure isn't just an anecdote. It's a stark, recent reminder of why understanding these engineering principles is absolutely critical.
For you, our curious listener, I think this deep dive really shows that even in fields like civil engineering, which might seem mature, there are always new complexities bubbling up, especially as we innovate. And there are always new solutions being discovered. It's a powerful reminder, isn't it, that good design is just as much about deeply understanding the vulnerabilities as it is about celebrating the strengths.
Absolutely. And maybe the bigger picture question that leaves us with is this. In a world pushing for ever more innovative, efficient structures, how well do we truly understand the nuances of how they behave under stress? What responsibility do designers and engineers have to use these more advanced tools like FEM to guarantee safety, especially when stepping away from standard designs? What further questions does this deep dive spark for you about the buildings and bridges you interact with every day?